Welcome back. We have a new section we're going to talk about, section 6.4, and the title of this section is Exponential and Logarithmic Functions. And the really new thing here is logarithmic functions. We've sort of talked about exponential functions, but here we're really going to concentrate on logarithms, what they are, how we use them. Remember on our videos, whenever you saw Baby Yoda, you knew we were talking about rational functions. And rational functions are these functions where you have some polynomial over another polynomial. It's a ratio, so rational functions. And whenever you saw the Little Women, the March sisters, you knew we were talking about exponential functions. And these are basically of the form y equals a times b to the x, with that initial value and then that change factor. So we need a new reminder of when we're talking about logarithmic functions, because this is a new topic. So we need a new picture, and for this one, this is the brand new one. For this one, I really liked this saying that my daughter sent me. What a good day to be proud of all the progress I've made. Each of you has made a lot of progress. We're at the end of the course, really close to the end, and I want you to be proud of how far you've come so far. And of course, keep going. So this is what, whenever you see this saying, you know that we're talking about logarithmic functions. Okay, the first example I want to look at in this section has to do with the population of Bangladesh. So Bangladesh is this country real close to India, and even though it's small, it has a lot of people. The population of Bangladesh T years since 2005 is modeled by P of T equals 141.8 times 1.018 to the T in millions of people. When will the population be 200 million? Okay, so this function, this population function, this looks like something that we're familiar with. This is definitely, well, think about what kind of function is this? With the variable in the exponent, it is an exponential function. And just like any exponential function, we can read off the initial value and the change factor. So this function is telling us that 141.8, and it's millions of people, is the initial value. And that means that's how many million people were in Bangladesh in 2005. Okay, the 1.018, this is the growth factor. And we know it's growing because that number is bigger than 1. Anytime this number is bigger than 1, it'll be growing instead of decaying. It's not growing super fast, like it's not doubling or tripling, but this number, when you get really big numbers like 141 million, it can make the population grow and grow and grow. Okay, so the question is, when will the population be 200 million? Okay, when will the population, so when is P 200 in this function? So when is 200 equal to 141.8 times 1.018, and we're asking when, so we're looking for this t. And we're going to try to solve this function. So let's see, we want to isolate the variable, which means maybe a good place to start would be to divide both sides by 141.8. So 200 divided by 141.8 gives us 1.41044 about, we'll round. And these guys cancel. We're left with 1.018 to the t. And now we just want to know what t is. Well, this is a little bit tricky to solve this equation. When your variable's up in an exponent, it's a little bit harder. We need a different strategy to solve this. So we're going to pause this right now. We'll come back to it. So we're going to come back to this because we need some more tools before we can solve this. And so let's change gears for a minute and look at some examples. If I tell you that 4 to the x equals 16, then, and I asked you what x is, x equals the exponent on 4 that would create a 16, that's 2. Okay, if I tell you that 2 to the x is 32, let's see, the power on 2 that would create a 32, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th equals 32. So 2 to the 5th equals 32. I've solved that. X equals 5. Okay, what if I say that 5 to the x equals 200? Could we solve this for x? Well, I'm going to have to think about this for a minute. I know that 5 squared is 25, and 5 cubed is 125, and 5 to the 4th, that's 625. 5 to some power equals 200. Well, it's between these guys, so it's not some nice round number. So all I know is x is between 3 and 4 somewhere. And without a calculator, I can't really come up with anything more precise. So x is between 3 and 4. And that's as precise as my brain can get. Without a calculator. Okay, so I'll take this as my best answer. Let's try one more. What if I say 3 to the x equals 10? Okay, well, I know that 3 squared is 9 and 3 cubed is 27. So whatever number this is, it's going to be some decimal number between 2 and 3. Probably closer to 2 because 3 squared is 9. So I don't know what x is, but I know that it's a number between 2 and 3. And again, that's as precise as I can get. That's my best estimate without a calculator. Okay, so to solve this problem, to solve these problems, we're going to use a new tool called a logarithm. And I'm going to define it, and then we'll look at a bunch of examples of what it means and how we can use it. So if I write y equals log, L-O-G, with a little base b down here of x, so this is written as y, or this is read as y equals log base b of x. And I haven't told you what it means yet. This is equivalent to or can be rewritten as b to the y equals x. So it's another way of saying this exponential relationship. And this is how we'll think of logarithms. So this is a really important relationship to remember. It means y is the exponent we place on b to get x. So we really want to remember, and like any new topic, it's going to take some getting used to this notation and some practice to really understand and get comfortable with using logarithms. But just like riding a bike, you know, you can't do it the first time you get on a bike, but after a while it becomes more and more natural. Okay, we're continuing 6.4, and we want to remember this is the important relationship. That this statement is equivalent to this statement. So let's just get some practice going back and forth between exponentials and logarithms. So we're going to rewrite as a logarithm these statements. So 4 squared equals 16. So b to this number across the equal sign equals this that I'm taking the logarithm of. So if I'm going to rewrite this as a logarithm, it looks like this. Log to the base b of 16 equals 2. And this is always the pattern, that this little number, the base of the logarithm, raised to this power equals this number that you're taking a logarithm of. So 4 to the second power equals 16. If I was going to rewrite 2 to the fifth equals 32 as a logarithm, it would look like this. Log to the base 2 of 32 equals 5. So 2 to the fifth equals 32. Yep, everything's in its right place. So think through, if you wanted to write this one, how you would write it as a logarithm. LOG. And then what number goes down here? It's the base of the exponent. So it's the base of the logarithm is the base of the exponent. And 5 to the x equals 200. If I wanted to rewrite 3 to the x equals 10 as a logarithm, then I would get my base is 3, just like the base of the exponent is 3. Log to the base 3 of 10 equals x. The power of logarithms, and you're probably starting to see this, is that these exponentials come down. And that's going to help us be able to solve exponential equations. These are equivalent statements, and each of them has kind of strengths and weaknesses. But the nice thing is, rewriting this relationship as a logarithm, the variable is now down out of an exponent. Okay, let's try going the other way. So example, we're going to rewrite as an exponential. And we'll start with this one. Log to the base 7 of 343 equals 3. Okay, I'm going to rewrite it. I'm already in a logarithm. I'm going to rewrite it as an exponential. So rewriting as an exponential, we take this little tiny number as the base, so 7 to the third equals 343. And I've done what they asked me to. Same relationship, just written two different ways. Log to the base 4 of 1 over 256 equals negative 4. And rewritten as an exponential, this says 4 to the negative 4 equals 1 over 256. We're not solving any equations, we're just rewriting things. So I want you to think of this as, you know, if you're going back and forth between English and Spanish, the word for apple is manzana. The word for tree is árbol. You can go back and forth to English, from English to Spanish. These are representing the same thing. An apple is the same thing as a manzana. It's just two different ways of expressing the object. A tree is an árbol. They're the same thing, but in certain situations you would use this language. In certain situations you would use this language. It's the same idea. This is the same statement as this. It's just in a different form or a different language. So when you say 5 squared equals 25, that can be rewritten as log to the base 5 of 25 equals 2. And this is in exponential form, and this is in logarithmic form. But you really are saying the same thing in a different way. Okay, so these are just the two languages that we're learning, that we're using. Okay, let's try a different kind of example. We're going to evaluate some logarithms without a calculator. So evaluate without a calculator. And the first one that we're going to do is evaluate log to the base 2 of 32. All right, the way logarithms work is I know that this little number raised to this power has to equal this number. So 2 to what power equals 32? 2 to what power equals 32? Well, this must be 5. And I've just evaluated that logarithm. Okay, let's try another one. Log to the base 8 of 1 over 64. Okay, they want me to evaluate this. I can't use a calculator, so I think again, what would this look like if I rewrote it as an exponential? Well, that would mean 8 to this power equals 1 over 64. So 8 to some power equals 1 over 64. I know that 8 squared equals 64, but I need 1 over 64. So it's not 8 squared, but it will be 8 to the negative 2. And that'll get me the reciprocal of 64. So 8 to the negative 2 equals 1 over 64. And this is the answer. This is evaluating this logarithm. Let's try a few more. How about log to the base 10 of 1,000? So what number can I put as an exponent on 10 to get 1,000? 10 to some power equals 1,000. Well, 10 squared is 100. 10 to the third is 1,000. So this logarithm equals 3. Let's try log to the base 10 of 0.01. Okay, 10 to some power. So I have to think for a minute, well, what is 0.01? 0.01, if I wrote it as a fraction, whoops, is, I know 0.1 is 1/10, so 0.01 is 1/100th. So 10 to what power would equal 1 over 100? This is kind of similar to this one over here. I know 10 squared equals 100, but 10 to the negative 2 will give me 1 over 100. How about log to the base 5 of 5? How would I evaluate this logarithm? 5 to what power equals 5? It's 1. Yeah, and that'll be true of any logarithm. Whenever your base is equal to the number that you're taking the logarithm of, it always equals 1. One more, log to the base 6 of 1 over 36. Six to some power equals 1 over 36. 6 squared is 36, so again, this is similar to some other ones. 6 to the negative 2 equals 1 over 36. All these logarithms we could do in our head. There are some that we won't be able to, and we'll talk about those in just a minute. One very important rule that we're going to use, it's a very powerful rule with logarithms. Is this rule. If you have, okay, so this is our relationship that we want to remember. This is like the Rosetta Stone of logarithms and exponentials. This is how you translate from one to another. But getting back to our important rule, if we are taking the log of something, and we have it to the base b, but the thing that we're taking a logarithm of has a power, so we're taking the log of this, you can actually bring that power out front and multiply it by the log in this way. This power rule of logarithms is one that we'll use to solve a lot of exponential equations. So this is called the power rule of logarithms, and we definitely want to remember this. So if you're taking the logarithm of something with a power, the power can actually be brought out front and multiplied by the logarithm. So this is very useful. Let me give you some examples. So if I say that, first let's just get some practice using it before we solve anything. If I'm taking the log of x cubed to the base 4, this can be rewritten as this power can come and be multiplied out front. So it can be written as 3 log to the base 4 of x. Or if I had log to the base 10 of 5.43 to the t, this power can come out front and be multiplied, and it's equivalent to t times log to the base 10 of 5.43. And we'll see soon how useful this is. Before we dive into using this, we do need to talk about the number e. The number e is an irrational number and goes on forever, but here's a decimal approximation of the beginning of it. This is an awesome number. It's an irrational number. Like pi, it has many places that it pops up in the real world. So e is an irrational number. It's also called a transcendental number, and it's a constant related to growth. And so it is an important number to talk about when we're talking about exponentials or logarithms, because growth is exponential functions are a good model for a lot of types of growth. Okay, so now that we know that, let's define a couple other things. There's two really special logarithms. If you look on your calculator, you'll see some log buttons. Here's a log button, and you don't immediately recognize this as a log button, but ln is another log button. And these are the two most common types of logarithms. And so let's talk about what they mean. The common logarithm is a log with base 10. And it's written as log x. And then there's a logarithm called the natural logarithm. And the natural logarithm is a log with base e. It's a logarithm with base e, and it's written as ln x. And the n is just a reminder that we're talking about natural. And I'm guessing they call it natural logarithm because it does show up in so many real-world applications of growth. Okay, these two logarithms, these are the two logarithms on your calculator typically. So when you see a logarithm and they didn't write a base, it means that it's base 10. And when you see ln, that is a log to the base e. Okay, we're starting to have some really good tools. We're still talking about 6.4. This is the translation between logarithms and exponentials, and this is the really powerful rule, the power rule of logarithms that we're going to use. And remember to be proud of all the progress you've made. You're doing great. I want to go back to this problem, the population of Bangladesh. We were trying to figure out, based on this exponential function, when the population will be 200 million. So back to this problem. When will the population be 200 million? So when does 200 equal 141.8 times 1.018 to the t? And it's that t that we're looking for because we're asking when. And we started the problem earlier. We decided that we'd divide both sides by 141.8 because it would cancel here. And this, when we can put it in the calculator and get that this equals 1.018 to the t. Now, and then we were stuck there. But now that we have logarithms, we're going to use this power rule of logarithms and solve this equation. And this is what I'm going to do. This is an equation, so as long as I do one thing to the left side, I can do it as long as I do it to the right side. I'm going to take the logarithm of both sides, and I'm going to take a log to the base 10. So the common logarithm, I'm going to take a common logarithm of both sides. And so I'm going to say log to the base 10, but when it's base 10, I don't have to write it. Of that should equal log of this, since they're equal. Log of this equals log of this. Okay, now I'm going to use the power rule that says, actually this power here you can bring out front with logarithms. So the log of 1.41044 equals t times the log of 1.018. This is way better because now I can actually divide both sides by this logarithm. Now, log has to stay attached to the number that you're taking the logarithm of. These aren't separate things. This is a function. So a common error I see students do is sort of separate logs from the numbers. But these are totally super glued together. When you take a logarithm, you're taking a logarithm of something. So the log and the number have to stay together at all times. So 1.018. And I'll divide this side by the same thing, 1.018. This goes away, this goes away. Now what do I do with this? The nice thing is on the right side all I have is t. Well, this is the great thing about a common logarithm. The base 10 logarithms are on our calculator, so we're going to actually just find the log of 1.41044 and divide it by, let's close that parentheses, and divide it by parentheses log of 1.018. Okay, so I found out, and that number is 19.28. I just solved the equation. I found out what t is. And a problem that I couldn't do a few minutes ago, I can do now because of logarithms. So let's see what this means for the problem. If t equals 19.28, and year 2005 is the beginning, so we'll add 19.28 to that, and we get 2024.28. Okay, so this tells me that in the year 2024, the model predicts Bangladesh's population will be 200 million. Great. Okay, so the two new tools, the two ideas is I took a logarithm of both sides and then I used the power rule of logarithms to bring that variable in the exponent down. Let's try a couple more problems similar to this. So solve the equation. Say that I had this equation, 4 to the x equals 0.015625. Well, in the olden days, a few minutes ago, I wouldn't know how to get this variable down. But now I'm going to rewrite as a logarithm. Actually, I'm not going to do that. I'm going to take the log of both sides. Take a base 10 logarithm of both sides. Okay, so log to the base 10 of 4 to the x should equal log to the base 10 of 0.015625. Now the power rule of logarithms enables me to bring this down. So x times log of 4 equals log of this. And I'll divide both sides by log of 4. Remember, a logarithm can't exist on its own. It has to have a number that it's taking the logarithm of. And x equals this number. So log of 0.015625 divided by log of 4. And x is -3. I'm going to do a quick check. I'm going to see, does 4 raised to the -3 really equal that? Yeah, it does equal this number. 4 to the -3 equals this number. So I found out what it is. All right, let's try one that's a little trickier. Let's say we have 2 to the 7x plus 5 equals 20. And again, we want to solve the equation, so we want to find out what x is. So let's try to get x as much by itself as we can. and then we'll use logarithms, and we'll subtract 5 from both sides. So 2 to the 7x equals 15. At this point, we'll take the log of both sides, and we'll take a base 10 logarithm. Honestly, I could take a natural logarithm also, because that's a button. I mean, that's a function that my calculator does really quickly. So either one, you could take a base 10 log or a natural log of both sides, and the calculator will help you evaluate that. Okay, these two things are equal, so the logarithms of both things are equal. Log of 2 to the 7x equals log of 15. I'm going to use that power rule of logarithms to bring this out front. And then I have 7 times x times log of 2 equals log of 15. Looking good so far. The awesome thing is x is now down out of an exponent, so I can just divide things off and get it by itself. I'm going to divide both sides by, let's see, I have 3 things multiplied together. I'm going to divide by 7 times log of 2, both sides. These cancel, this cancels. I'm left just with an x here. So x equals log of 15 divided by 7 log of 2. And I'll do that on my calculator. So log of 15, and then I'm going to take that number and divide it by parentheses 7 times log of 2. And I get x is about 0.55813. I've solved the equation. I'm going to double check it. I'm going back to the original. So that number times 7. So 2 raised to that answer is that. And if I add 5, yeah, I get 20. So that checks out. So you're already seeing that logarithms help us. It's a great tool to solve equations when the variable is up in an exponent. And so we want to start recognizing this. Like in these last 2 examples, I never said use a logarithm. All I said is solve this equation. But when there's a variable kind of stuck up in an exponent, using logarithms is a strategy that's really helpful. So logarithms are a powerful tool that we can use to solve equations when the variable is up in an exponent. Now we're going to solve some equations, some logarithmic equations. So again, we're solving the equation. So find out what the variable is. And our first example will be natural log of x equals 2/3. Okay, so to solve this, I'm going to rewrite it as an exponential expression. And well, first of all, I'm going to remember that this is just log to the base e of x equals 2/3. Okay, rewriting it as an exponential, this means e to the 2/3 equals x. E to the 2/3 power equals x. Okay, I can totally solve that because x is just whatever this is, and I'll use my calculator. There's a little e to the x button. Whoops, not that one. Second, e to the 2/3, so parentheses 2 divided by 3. And I find out that x equals 1.95 about. Let's just try that. Let's check it. So does the natural log of 1.95 equal about, no. Oh yeah. Equal 2/3. Yeah, it's pretty close. It's not exact because I rounded. Okay, for extra credit, if you want to message me the name of just one of your favorite local restaurants. I'll give you 3 homework extra credit points. All right, let's solve this equation. Natural log of 2 over x plus 5 equals 7. And again, we're going to think of this is just a shorthand way of writing log to the base e of 2 over x plus 5 equals 7. And we need to solve it for x. So we rewrite as an exponential. And it becomes this little base to this power equals this. So e to the 7th equals 2 over x plus 5. And this is an equation I can solve. So I want to find out what x is. I'll multiply both sides by x plus 5. Cancels here. So x plus 5 times e to the 7th, that's just some number, equals 2. I'll divide both sides by e to the 7th. Cancel, cancel. So I have x plus 5 equals 2 over e to the 7th. I'll subtract 5 from both sides. So x equals 2 over e to the 7th minus 5. Let's find out what that is. 2 divided by e to the 7th is that, and then subtract 5, and I get x is negative 4.99818 about. And I've solved that equation for x. Both of these logarithmic equations I rewrote as an exponential. So I just translated it into exponentials. Okay, this is a great example. The important bacterium E. coli has a doubling time of 17 minutes at 98.6 degrees Fahrenheit. Consider an initial count of 1,000 bacteria. The growth of the bacterium can be described under these conditions by the function n of t equals 1,000 times 2 to the t over 17, where t is time in minutes and n of t is the number of cells of the bacterium at time t. When will the initial 1,000 bacteria grow to be 5 million bacteria? Okay, so nice thing is they've given us the formula already. And what we want to know is at what time t does n equal 5 million? All right, so 5 million is the number of bacteria equals 1,000 times 2, and it's this t that we're looking for. When does it happen? Divided by 17. So we have to solve this equation, and this is an exponential equation. The variable is up and then an exponent. So we're going to clean it up a little bit and then use logarithms to solve it. And we'll start by dividing both sides by 1,000, just to try and get as much as we can away from the variable. Okay, 5 million divided by 1,000 is 5,000. And I got to double check that. There's so many zeros. 5, 1, 2, 3, 1, 2, 3, divided by 1, 1, 2, 3. Yep, 5,000. Okay, and we still have 2 to the t over 17th power. Okay, we have a variable trapped up in an exponent. We're going to take the log of both sides, and we'll use common logarithms. So the log of that has to equal the log of this, since they're both equal. Now we're going to invoke the power rule for logarithms, and we're able to take this power on the 2 out front. So the log of 5,000 equals t over 17 times the log of 2. And that's great. Now our variable is kind of out of an exponent. We're just going to clean it up. We'll divide both sides by log of 2. And so we have log of 5,000 divided by log of 2 equals t over 17. Multiply both sides by 17. So this is what t equals, and we just need to make sure that we cleanly put it into the calculator. 17 times log of 5,000, and then we'll divide that by log of 2. And we find out that t equals 208.9 approximately. What does that mean? Let's see, t was in minutes. So this bacteria is growing pretty quickly. And what started out as 1,000 bacteria grows to 5 million bacteria in this many minutes. That's pretty quick. So in about 3 hours and close to 29 minutes, the bacteria population is 5 million. That's really quick. Before we conclude talking about logarithms, I do want to look at what the graphs of these logarithmic functions look like. So this red line is the graph of the function natural log of x. And remember that that's just log to the base e of x. So logarithmic functions all follow a similar pattern where they're actually all the basic ones like this are all going to go through the point 1, 0. As you approach 0, the logarithm is going to go off to negative infinity. And as x gets larger, the logarithm also gets larger, but nothing like an exponential function. It grows, but grows slower and slower as time goes on. Just to compare, here we have the natural logarithmic function in red, and this is log to the base 10. So again, this is like f of x equals log to the base e of x, and then this blue one would be like the function log to the base 10 of x. So they both have the attributes that we talked about a minute ago. As you approach 0, as x approaches 0, they go off to negative infinity. They go through the point 1, 0, and they both grow as x grows, but they grow less and less quickly. Let's talk about why this is happening. Why are they all going through this point? Why do logarithmic functions go through the point 1, 0? And remember, this is our input value. So why, when x is 1, does y have to be 0? Talk about why this would be true. So let's look at this first function, log to the base e of x. So if we put in 1 for x to log to the base e of x, that would be like putting in 1 for x. So evaluating this logarithm, log to the base e of 1 equals a number that when I raise e to that number, I'll get 1. E to what power equals 1? It's 0. So when my input is 1, my output is 0. Let's look at the logarithmic function to the base 10. G of 1 equals log to the base 10. Again, my input is 1. So what power could I raise 10 to? 10 to some power equals 1. Well, you see the pattern. Whatever your base is, anything to the 0 power will equal 1. And that's why all of these logarithmic functions go through the point 1, 0. Last thing is I want to show you this green function along with y equals natural log of x. So this is y equals natural log of x, which is the same as log to the base e of x. This function right here looks symmetric to the line y equals x, which is an indicator that it might be the inverse function of our red logarithmic function, and it is. This green function here is the function y equals e to the x. This is an exponential function. This is a number raised to some variable power, and it is the inverse function of natural log of x. I just wanted to introduce this idea that exponential functions are inverse functions of logarithms and vice versa. And that bears out when you look at the graphs of each of these. So they definitely go together, these two types of functions. All right, good job. This is a lot of information, but you have enough to do the homework, and good luck.